some kind of requirement. I went to Nagpur. I was staying outside for some time.
Okay.
So we'll come to your lab, sir.
Sure.
Yeah. We'll discuss with you accordingly.
Sure. We'll wait for some time. Let others also join, and then we'll start.
Yes, sir. Yes, sir.
And meantime, you can just see that whether you can share the slides, and then I'll going to make some few minutes, 5 minutes, some presentation. After that, you can start. Right now, you can just check whether you can share the slides.
Yeah.
Lakshmi, can you inform all others to follow up with the student?
Yes, sir.
My slides are visible, sir.
Right. Yes, visible. Yes, correct. Go, just move. Yes.
Slides are
Yeah.
moving.
Yes, it's going good. Very nice.
Okay, then now I mean stop sharing. Then we'll.
Yes, sure. Yeah, there are some people waiting in the lobby, it seems. Could you please ask them to join? Just take care of that. Yeah, I'm in a talk. I'll call after some time. Okay. Lakshmi, or Priya, can you just share this announcement in whatever we made through WhatsApp? Or Mekala can send me.
Yes, sir.
Oh, Mekala sent it to you. QRL list is there. Okay, we'll start. Saravanan, are you ready?
Yes, sir.
Okay,
I'm ready.
we'll start. I'll just make a small presentation. After that, we'll start.
Yes, sir. Yes.
Okay, Gupta ji is also joined. Gupta ji, good afternoon. Welcome. So, are you all able to see my screen?
Yes, sir.
Okay, good afternoon and welcome to the Air Quality Management lecture series. This is the 68th lecture. We started this in 2020. So the idea of this lecture is to provide a platform for the young researchers, scientists, engineers, educators, and practitioners to share the latest advancement and theories and applications in the area of air quality management. And this is the first of its kind lecture series in India. And this also provides recent developments, innovations, and use recent technologies in addressing the air quality issues in urban areas and rural areas. Also provides platform for collaboration with stakeholders and experts from various countries. So these are all our previous speakers. You will see 67, expert. Now, in order to strengthen our air quality management activities, we also started Air Quality Management Association in 2022, and the main aim of this association is to, to provide an air quality, promoting some of these activities in the urban and rural areas, or also address the issues related to air quality, indoor air quality, health risk, and technological interventions and policy formulations. AQML also provides a common forum to interact with one another for mutual benefits. And if you are not a member of this Air Quality Management Association, I request you to join with this association and contribute to addressing the air quality issues of the society. And of course, we have an Indian International Conference on Air Quality Management. So this will be the 11th annual conference. This will going to happen in IIT Madras. This will happen from 14th to 18th December 2026. So please visit our website, and if you are interested to contribute research papers, please see the website and submit your abstract. So now today's talk will be given by Dr. G.Saravanan. He's a principal scientist at CSIR-National Environmental Engineering Research Institute, Chennai lab. So now I request Lakshmi to introduce the speaker.
Dr. G.Saravanan currently serves as Principal Scientist at the Chennai Regional Center, CSIR Madras Complex, CSIR-NEERI, India. He holds a master's degree from University of Madras as well as Master of Science and Doctor of Science degrees from Shinsu University, Japan. Dr. Saravanan has published over 45 articles in renowned scientific journals and holds 11 national and international patents. This innovative research has garnered significant recognition, with some of his work highlighted on the cover pages of leading journals. His primary research interest is the development of advanced materials for energy and environmental remediation. In addition to his scientific achievements, Dr. Saravanan serves as a subject expert for NGT hearings, offering expertise in environmental matters. He is also an active contributor to key national missions like CSIR Hydrogen Mission, the National Mission on Clean Ganga, and initiatives related to reduced emission crackers. Today's talk is titled Lattice-engineered catalyst for air pollution control. The talk presents recent advances in the design and engineering of platinum group metal and TGM-free catalysts for sustainable environmental and energy applications. It discusses how atomic scale lattice engineering and advanced catalyst architectures improve catalytic efficiency while reducing dependence on scarce and expensive noble metals. The presentation also highlights their applications in automotive exhaust treatment, indoor air quality management, fuel cell systems, and preferential carbon monoxide oxidation for hydrogen stream purification. The talk also details the scalable synthetic methodologies, advanced structural characterization, and real-world deployment of these engineered catalysts. We welcome you, sir, for the talk.
Yeah, thank you, Dr. Saravanan, for kindly agreeing in a short notice. Thank you. So I'll stop sharing.
Yes. Thank you, sir, for the wonderful opportunity again. And since like our interactions was last December, and it is really indeed a very pleasure to meet you, and I really excited to see your enthusiasm in various activities. So thanks again for the wonderful opportunity again. So I'm going to share the talk. Sir, my slides are visible.
Yes, it's visible.
So, yeah, it is indeed a great initiative, and especially the country like ours, like facing a lot of issues. So, we need management as well as control solutions for air quality across country. So, it is a right time that this kind of initiative is paid for our country. So, today my topic is on lattice-engineered catalysts for air pollution control. How lattice level engineering will aid to improve the catalytic performance for automobile exhaust fuel cells and the hydrogen cleaning of hydrogen stream. This kind of some of the work that we have done in our lab. So I'm going to share some of the findings on this topic. So before going to discuss the topic, and I wish to introduce about NEERI. CSIR-NEERI was established in 1958. It's due to jaundice epidemic. That time, NEERI name was CSIR, Central Public Health Engineering Research Institute. Later, 1974, it was renamed as NEERI. Exactly like air pollution related issues started emerging across the world globe. So it's a country thinks about that, and the countries changed as CSIR to NEERI to focus all environmental matters. So initially, our mandate was water and sanitation. Now deal with almost all environmental related issues that we are facing. So our vision is to be a leader in environmental science and technology for sustainable development. Our mission is to provide innovative and effective solutions for various stakeholders, including government and industries, especially to support 800 million underprivileged people in the country. So our current mandate is to be to do R&D with various environmental science and engineering, to be part of various mission projects of where countries are developing. In fact, we are part of hydrogen mission and Ministry of Missions controlling of critical minerals, and those important missions that we are part. And this is the journey of CSIR-NEERI. Since its inception, it's focused on mostly water matrices and various water-related issues. NEERI was focused and tried to address the various problems in emerging in water. Later, 1974. After that, it is like global revolution happened. It's a lot of industrializations happened. That time, air pollution started emerging. Our flagship activities was on is like monitoring air quality at Taj Mahal and from Kolkata to Taj Mahal, and of course various fugitive emissions from various states, and stake emission. These are the various important activities on that type. Later, NEERI focused to have, impact assessment report. This before, implementing any industrial-related activities. NEERI is focused on to have EIA and the LCA studies so that we can understand what are the possible issues that even the industries is started, is coming out so that we can control the possible issues before. Now, after 2000 onwards, the various mission activities that we various technologies developed and deployed across country in this way. So this is the our how to say forte in various environmental matrices, starting from air pollution to water and including health and toxicity. So we have 5 regional centers across country: Delhi, Chennai, Hyderabad, Kolkata, Mumbai, and we started race facility at Sivagasi to support the fireworks manufacturers, as a lot of issues in that fireworks manufacturers, and we are currently having facility at Sivagasi to address the problem of fireworks manufacturers. So we focus most of the SDGs and either directly or indirectly. Since being in environment, we need to be associated with the to be part of SDGs. So this is the activities that we do at in Chennai Regional Center, starting from monitoring to modeling and simulations, followed by management and control. In the control aspect, I'm focusing on we develop the various cutting edge materials for both water and air pollution control, and we have the biological team to contribute this kind of to activities. This is the area that we focus. We focus mostly on environmental remediation materials for automobile exhaust purification and the energy materials, both catalyst development for both cathode and anode. We also focus on generation of clean energy from fossil fuels, especially for thermal power plants. In addition to that, we focus on water. Today, I'm going to focus this material development for both automobile exhaust and the energy materials. In addition to that, we were part of to characterize the various water and sediment of River Ganga to understand its special property, whether how it is. This non-putrefying property of River Ganga. So, what are the possible reasons to have the special property? So NEERI involved try to investigate scientifically what is the reason to have that special property. So our report is now is decorated in Parliament, so that the lot of finding that we have done in this work. This is very recent activity. We are trying to generate reduced emission crackers to. Especially we have the issues in the air pollution. So we try to understand the composition and emission relationship so that we can give the better composition with the less emissions. So we are focusing intentionally to have the reduced emission crackers. This is works focusing, and we are focusing at Sivagasi. So coming to the topic, we are. This is the energy status of our country. This is the comparison of year 2000 and very recent in 2019. If you see that all this one, our energy status, our is changing. If you go for GDP, it is much higher, almost double when compared to year 2000. If you see the energy demand per capita, oil, whatever oil energy related thing, we are having much higher than, almost double than this one. So eventually, when you are consuming this kind of energy as well as fossils, we are emitting CO2, and the CO2 emissions per capita is higher. Although per capita is higher, but when compared to international countries like developed countries, we are not much higher, and which is less than 2% when you compare to the developed countries. Here, this is the energy. Generation of various industries. If you see all these sectors, our energy mix is basically depending on fossils. not only in, I mean, industries is a coal, oil, and electricity. Electricity is again from, coal. Transportation is mostly from oil, and the building is again, so mostly depending on, fossils, and a little bit, bioenergy and other renewables are there. But our across sectors we are depending on, fossils as of now. And this is the energy demand. Energy demand is also again we are depending on fossil fuels, and this one will be continuing to increase with increasing years. And this is a projection. Okay, this is up to 2026. We are in up to this level, and when we are coming to like a coming years 2042, our energy depending again is a fossil based only, and eventually we are going to emit a lot of greenhouse gases. By this is the energy outlook compared to coal. Whatever the consumption today, it's going to be 2 times higher than whatever we are consuming, I mean, today. And the gas, it will be like a 3 times, and the oil we are consuming 4 times, and the electricity again from the fossil fuel, it will be 3 times. So this will be the projections, and because our energy demand is much higher than this one, so our fossil fuel dependence will be much higher. And our government of India is like involving or to give the various initiatives to have renewables, and of course it will give a big competition to the fossil sector. But still we are depending on fossils. That's as of reality. By 2040, the coal share roughly will be the off when whatever we are using today. So more than 35%. Still we are going to use coal by 2040, and we are going to increase 100 times whatever the solar related renewables. It will be higher, more than 100 times whatever we are having this. So government of India is having cleaner energy ambitious scenario. It will be like by 2030 is 100% e-vehicles government is now targeting, and the oil demand will be the like end user level will be lower, but the total energy demand or total fossil demand will be higher. This is the global mean temperature and the consumption of fossil fuels. This one, and the global mean temperature is up to before or pre industrialization era. So up to 1970s is not changing much, but after post industrialization era, it's increasing with increasing years. And this is again consumption of fossils is increasing after 1970s. So this was like this one. Then later EPA came into the picture, and they have given a lot of recommendations and norms across world to have to keep the control of global mean temperature. So this is the CO2 emissions of across sectors, and the total emissions is increasing, and it's expected to increasing. So this is the Niti Aayog data. We are going to, it's for sure, as this data tells that we are going to emit carbon dioxide in coming days, indicates we are going to consume fossils. Our energy will be dependent on fossils. So let's take as an example diesel as a fuel, and what is happening. So if you see that, Society of Indian Automobile Manufacturers, if you see that the production rate, selling rate is increasing with increasing year, and eventually we are emitting, greenhouse gases, which is having a lot of issues. And if in case of diesel, we are emitting diesel particulate matter, which is having a lot of issues. So this is, and now diesel vehicles in NCR region, it's now banned. But whatever the already vehicles are there, it's still we are using diesel. It's having a lot of health impacts. So when it's the particle size, when it's a smaller one, it's going to our deep lung, and it's creating a lot of issues in our health. And there are a lot of other issues. It can decrease the harvesting efficiency, and it has create the acidic rain, and all other issues are there. And it has a black carbon effect, and it is when especially in the winter season, when you are having started consuming all fossil fuels, it is having the reduced visibility, especially the post Deepavali. This all the other in addition to the stubble burning and all this, the crackers and automobiles, construction sector, everything clubbed together, and it's giving a lot of visibility issues. So we need to do something on that. So and of course, a country brought a lot of emission norms, and India, these norms, indicates our commitment towards the environment. So we started India 2000 as a Euro 1 norms, and this is the various, pollutant concentration. If you see these things, and the steep, they are, reduced within 15 to 17 years, and there's a very more than 2 to 3 times. All the things are decreased, and we bypassed for Euro 5. That means Bharat Stage 5, and we adopted Bharat 6 within 3 years. We started, and now currently we are having BS 6 norms across the country. So now we are going to have scrap policy, but because of COVID, it got delayed. But soon this scrap policy also will come. That means the old vehicles, we are going to scrap it, and we are going to have, vehicles which are emitting very less, emissions. That is the thing. So so now it is sure that we are having a lot of, we are depending a lot of fossils, and we are emitting lot of greenhouse gases. It is eventually is highly stress to the humans as well as environment. So we have to do certain things to take care of these emissions, either post treatment devices to have, so that we can control these toxic gases, so that we can have environment friendly society, or we have clean energy devices, so called fuel cells, so that we can have cleaner energy. And this is much better than IC engines, which is having efficiency is much higher, starting ranging from 50 to 90% performance is there. So that fuel cells is considered as futuristic energy devices which can control greenhouse gases. So I'm going to focus now post or after treatment emission control technologies for diesel particulate matter. So there are a couple of important technologies are the DOC, diesel oxidation catalyst, or DPF, diesel particulate filter. Especially after post combustion, we have hydrocarbon and carbon monoxide soot, that means particulate matter, and the NOx. These are the possible major emissions from when we are combusting diesels, and this need to be taken care. For that, we need some catalyst, so that we will be controlling, or will have, releasing the less toxic gases to the environment. So diesel oxygen catalyst, it is the efficiency is reasonably better, 20 to 30% efficiency, but particulate matter still is going to the issues, and it has we need, all this is depending on platinum, and we have to take care of platinum, because there are some certain issues which I am going to discuss in coming slides. So in the diesel particulate filters is again there, and these are the but the particle matter can only be oxidized above 500 degrees centigrade. So but most of the exhaust temperature is roughly below 500 degrees, so that you need to have supply additional energy, so that you can take care of those particulate matter, so which is highly energy intensive process. In addition to that, these performance related issues, and the catalyst that we are using conventionally, it is a platinum. It has a lot of problem. It is after catalytic applications, when you apply certain conditions, the particulate catalytic particles, which is roughly 2 to 3 nanometer size, which we are generally people are using. After this exhaust treatment, the particles are get agglomerated. So then once it's agglomerated, this performance of the DOC or DPF is steeply reducing. So this is, we can see that when our municipal buses, very very old vehicles, when the driver started, we can see it's a dense smoke once we after starting that vehicle. This is because that inefficiency of that catalytic converter or automobile exhaust. So that is the reason we are seeing this one. So that simply the CatCon is not working in this one. So there are a lot of other things other because of these agglomeration issues, and we need to find something better catalyst than platinum, which is having less agglomeration, as well as some other cost related issues also we have to address. So if you see the platinum group metals and generally it's all like we are using the various catalytic related applications, not only like indoor and outdoor, and the energy materials and the water, everything is we are using the platinum and platinum group metals. And this is, if you see this cost is quite like a highly fluctuating, and depending on its resources, depending on it's highly fluctuating. The cost is going to be a serious issues, and considering the number of vehicles that we are going to have, we need a lot of platinum group metals. And this availability of these platinum group metals are very limited, and it is available only at localized regions of the world. And especially like South Africa is having predominantly they're having these reserves, and other countries are having very less amount. In India, we don't have any other amount. So we have to do something to take care of those platinum group metals by using current science and technology. In addition to that, as I pointed out, the conventional catalyst, whatever we are having is after certain applications, we are having less active surface area, and it's undergoes a corrosion, and the stability again is the issues. So we have to address, when you develop the catalyst to take care of those emissions, we have to address this problem also. So what is the possible solution to address these things? So we have as I pointed out, we have three important metal is contributing most of the automobile exhaust. And ultimately, we need to find some non-PGM catalyst, which should have the to take care of the target applications. But that is eventually it's the lot of R&D is required. So currently, what we need to do is we can minimize the amount of these PGMs, so that we can enhance the activity by using same or less amount of these PGMs, so that we can minimize the consumption. So there are certain approaches. One is develop alloy or intermetallic catalyst formations and the morphological controls. So what is required for typical diesel soot oxidation catalyst? It should be stable up to 800 degrees. The catalyst should stable and should be active at very low temperature. When we are taking the automobile exhaust, we call it like a cold start period. When we start the vehicle, we see a lot of dense smoke during the initial time, because of that CatCon temperature is not sufficient enough. So whatever after combustion of diesel or fossils is coming outside to the tailpipe, that's the reason we are seeing the dense smoke. Okay, so if CatCon active at very low temperature, preferably low temperature, it will be really better to take care of those toxic gases. Then whatever the particulate matter is there, and hydrocarbon, these things are supposed to give only convert into CO2. The hydrocarbon or particulate matter should not give CO, which is again another issue that it has health related issues. And catalyst should be stable. It should work for a pretty prolonged time, and chemically as well as stable. It should be like a lower cost. So one such approaches, we have developed intermetallic PTTI catalyst, platinum titanium based, all are in metallic form. We developed this catalyst to address this. To take care of diesel, carbon monoxide oxidation. So here we have developed a catalyst using silica as a support, and we have, with increasing of the silica support, we have very finely dispersed nanoparticles. The particle size is roughly 2 nanometer when we are, and this is highly homogeneously dispersed across the support that we are having. So this is the typical catalytic performance, and this one is 0.5 is the platinum loading. The same loading weight, when you see this activity, the intermetallic phase of PTTI, this combination is much higher activity than the commercial or reference platinum. when we are increasing the double the amount of platinum, still the activity is much better. As I pointed out, we have to minimize the platinum consumption. That's what this area achieving this intermetallic phase between PT and TI, which is having the much better activity than your pure platinum, which is we are the, it's showing that it's addressing our concern. When you see this compared to all other the working temperature and the intermetallic catalyst PTTI is much better than this one. So when we are keeping titanium in the lattice of platinum, it's really taking care of it's changing the electronic structure of platinum, which is the facilitate CO oxidation. So after checking the several cycles, we need to see whether the the intermetallic is still stable or not, because that is the important criteria to have the durability, durable performance. And there are some catalysts showing the initial activity, but over time it is not. The activities will be like inferior over time. So we need to ensure that after several cycles we performed, we have kept this catalyst under these harsh conditions. We checked it. We found that its intermetallic phase between PT and it is just quite stable. Although slight agglomeration that we found, and we need to be address that one, but the important point is like the intermetallic phase between PT TI is quite stable, even after harsh exhaust conditions. Then the thing is, when we prepare this PTTA, you need very selective special conditions so that that you can able to achieve this PTTA intermetallic phase. But that is a bit difficult, and scalability is another issues in that one. So we thought we will go with a little bit commonly or abundantly available D block elements, so that for example copper, so that we can have the similar performance. So we have done PTCU combinations with various type of intermetallics. Here all 5 weight loading percentage, PTCU3, PTCU and PT3CU, we have done the model CO oxidation. When you see this, when you compare this catalyst, although these catalysts are having same loading weight, platinum is a 5 weight percentage, and this catalyst showing much better higher activity. Please note that the same loading weight, when you are achieving the different intermetallic structures, is having the different performance. So that means when you keep the certain element in the lattice of platinum, you can influence the electronic structure, which can have the better performance than the commercial platinum, as well as the same intermetallic structures. So here this is the different electronic crystal structures of of these PT-CU combinations. When you have achieved this kind of platinum and CU intermetallic structure, it's showing much better activity than these other two. And we, as usual, we performed post-mortem analysis of after catalytic reactions, and we found these two PT3CU and PTCU combinations showing the same pace, whereas the PT CU3 is not stable. So that means it is not recommended for these applications. So you can go with this one of these two. But when we see that the morphology after the reaction, the particle size is almost closer to the initial size, roughly 3 to 4 nanometer. That means the PT3CU combination is capable of oxidizing CO under even this given conditions, and you can have something. So, but PTCU, the although phase structure, intermetallic structure is stable even after exhaust conditions, but it is the particle size is increasing when compared to the initial size. And as usual, and the PTCU3 is the both phase as well as got agglomeration. So when you are keeping copper, the maximum amount in the lattice of platinum is not recommended, but very little amount of the PT3CU combination is showing better performance as well as a durable. Performance is durable. As I said, we can minimize the platinum consumption for these applications, and eventually we should target non-precious metal-based catalysts, and which should have the better diesel particulate matter performance, which is people are looking. And we have developed manganese substituted strontium ferrite is a perovskite structures which is more capable of taking care of diesel particulate matter when compared with commercial platinum, as well as, anyway, I will show some of the results of this. So we selected perovskite catalyst. Actually, the perovskite based catalyst people have been using for quite some time back. Because of the presence of lead, and the sulfur in the gasoline, this started. Stability of this catalyst become like a questionable. So people haven't used for only R&D or research purpose. People have used. But because of the improvement in sulfur as well as lead in gasoline, there are renewed interest to use perovskites for automobile exhaust applications, and it has quite merit when you're going with it's quite stable because the phase formation temperature is above 800 degrees generally. You can play with the shape and you can tailor on the A and B side, and you can have the scalability, and it is generally low cost. So there are a lot of merits are there. So we selected perovskites for diesel particulate matter oxidation. So synthesis is quite simple. We can take appropriate salt, whatever that you are targeting, and take the stoichiometric and put some shape controlling and the agents and precipitate, followed by calcination and the target temperature. You will get the target phase. So we have prepared manganese substituted strontium ferrite, and when we have tuned the various compositions on this one, with crossing 20% of manganese, the pace is not stable, and we found the 10% of substitution at manganese, showing that better performance. So I have shown this one here. So generally after synthesis, we perform XRD whether the synthesized material is stable or not. And this is unsubstituted, this one. When we substitute the manganese in the lattice of strontium ferrite, this is a diffractopic shifted to the lower diffraction. That means the lattice is become expanded while incorporating of manganese. So for reference purpose, we have deposited manganese on because we need to know whether the lattice substitution the lattice of strontium ferrite influence the catalytic activity or not. So we have prepared the reference material for the same combinations with the same stoichiometric, but this is a manganese substituted oxide. Manganese oxide dispersed strontium ferrite we prepared as a reference material, and again as usual we performed XRD to ensure manganese oxide is on the surface of strontium ferrite and not in the lattice. This is a TM characterization. So when we incorporate manganese in the lattice, the particle size is become smaller. Okay, and we found the available surface is a 2-1-1 plane on the surface. This one we have done elemental mapping, and manganese is distributed homogeneously across all particles. That means manganese is inside the lattice of manganese. Of course, in addition to XPS, I'm telling this. So anyway, we have done catalytic evaluations, so both conventional fixed bed reactor as well as temperature probe oxidation experiments. So we have mixed catalyst, the strontium ferrite, manganese substitute strontium ferrite, and soot with this ratio, and we have selected tight contact conditions, and this is the condition that we have done this. So and we found this is the Printex. V is a model. Particulate matter, and strontium ferrite. This is a manganese oxide. This is a reference catalyst, and this one is like manganese substitute strontium ferrite. As I pointed out, we have to minimize the temperature when compared to automobile exhaust of like 500 degrees. So this is a temperature window that which generally particulate matter can be oxidized. So this window supposed to be reduced so that you can have the better performance even at low temperature range. Nothing but cold start period. Okay. So when we putting the manganese in the lattice of strontium ferrite, roughly even around 300 degrees started showing the activity. So less than 400, 380 degrees centigrade, you can completely oxidize the particulate matter that we have, used. So manganese substitute strontium ferrite has the potential to take care of the diesel particulate matter oxidation. So as again we need to check this durability, and the manganese substituted is almost like showing the same potential. What we have done, we have taken the catalyst, we mix the diesel particulate matter. After first cycle, we mixed. So these are the things we continue and so on. We have repeated these experiments and we checked, and the performance is almost like within the desired window. So when we go for like a manganese oxide, this one, and so getting, performance getting inferior, shifting to the higher temperature window. So because of the manganese getting is like an agglomeration. Okay, and we have performed 5 cycles, and we found that this manganese substitute is showing the stable and reliable performance in compared with other other catalysts. So again, we repeated the various cycles. We checked the structural integrity as well as stability, and we found this both this unsubstituted and manganese substitute become stable. Nothing is happening even after certain cycles. Whereas in that manganese substitute got like particles got agglomeration, and showing that how to say, the particles get agglomerated on the surface. So once we realize that it has a potential, then we have developed a prototype using typical automobile exhaust using coordinate substrate. We have coated this coated this manganese substitute strontium ferrite, and we have loaded and we have checked the catalytic performance using actual engine dynamometer. This is a collaboration work from from IIT Kanpur that we have done. So we have checked this performance, and coming to the direct results, the blue one is typical commercial platinum automobile exhaust. People are using it. When we coat this material in the typical coordinate substrate, the activities is almost comparable. The commercial automobile exhaust having platinum, here there's no platinum. So that is the beauty of this work. At higher emission load, the catalytic activity is almost comparable with commercial platinum POC. So that is the important result that we found, and this work got patented. So now I focused automobile exhaust, now the post treatment this one, and we can focus on the fuel cells. I will show some of the some important results about the fuel cells. So we need a decentralized power. Please stop me when you your time is over.
No problem. You can take. So you will take another how many minutes?
Maybe another 15 minutes, 15 to 20 minutes.
Oh, okay. It's too long. It's fine. Can you just try to finish it by another 10 minutes, maybe?
Yeah. That's the reason. Okay. Yeah, I will finish by end up accordingly. Yeah.
Sure.
So we need. Thank you, sir. So we need decentralized power for various applications, and for the telecom industries, we are using more than 200 crore liters of diesel per year to supply power, so that we could be having telecom signal to our mobiles. So, but it has its own limitations, as we know. Its efficiency is less than 15%, and it's a problem for in terms of greenhouse gas and all the things. So we need to have the better energy devices which can give the better efficiency than IC engines. This diesel genset. So fuel cells can fulfill this one. Of course, there are certain issues are there. We have to address those problems also. So this is the typical, we are generating hydrogen from fossil fuels, and based on well to well and waste to wealth approach, and we are having how to say, after this one, and we are having reformer and followed by water gas reaction, so that we will be having hydrogen. When we are having this hydrogen, we are we are the hydrogen stream containing roughly 1 to 5% of CO, which is not desirable for fuel cells because people are using platinum for fuel cell as a catalyst, and we have to take care of that thing. So, and we have to either your catalyst need to work at even high concentration of CO, or the CO is supposed to be selectively oxidized in the presence of hydrogen. This is called preferential CO oxidation. So these two steps need to be taken care so that we can have hydrogen from fossils, so that we can run the fuel cells, and which is having much better efficiency than this one. Again, there are several. Still people are using platinum as a catalytic centers for both cathode and anode in the fuel cells, and because of certain limitations, as I pointed out earlier, we have to take care of these fossils. These catalyst platinum with. We need to minimize the less amount of platinum. So this is the typical, fuel cells with various type of, hydrogen direct fuel cells, and this, among all these things, oxygen reduction reaction is a very important step, which is a sluggish reaction, and it consumes a more amount of platinum. So we need to minimize the amount of platinum here, and I'm going to discuss this one. So this is the part of CSI hydrogen mission project that we have developed. We have targeted intermetallic phase of platinum and cobalt. Here we have increased the platinum loading up to 48%, which is required to take care of take care of sluggish reaction of oxygen reduction reaction. And we have ensured targeted phase on all the things. We performed XPS whether electronic structure is changing or not when compared to commercial platinum. We have selected commercial Johnson-Matthey platinum catalyst, and we compared we use that as a benchmark performance. And this is the typical TM analysis, and the particle size is like roughly 2 to 4 nanometer, and it is highly ordered structure that we got. And we performed ORR, oxygen reduction reaction. The dotted line is a typical commercial Johnson-Matthey catalyst. When you go with the PTCO, and PTCO3 is much better than commercial Johnson-Matthey catalyst. Okay. When we also check the CO striping characteristics using the Johnson-Matthey catalyst. As I pointed out, commercial catalysts, if the CO gas is present in the hydrogen stream, it can absorb, and it is showing activity will not be there if there is a CO. But the catalyst that we developed here is there's no CO absorption on the surfaces, so that this is again CO rich conditions. Also, this catalyst will work under these typical fuel cell conditions. So we have checked the stability of this catalyst. Of course, both catalysts showing the inferior activity, but when compared to commercial Johnson-Matthey catalyst and the catalyst that we selected, we prepared in our laboratory, showing much better at any of these tested cycles. And again, we need to check that stability of the catalyst after 10,000 cycles. The fresh catalyst having roughly 2 to 3 nanometer size. When you go for after 10,000 cycles, the particles get agglomerated. And here also is a kind of agglomeration is there, but not agglomerated as like commercial Johnson-Matthey catalyst. So the PTCO combination is really better for oxygen reduction catalyst. And another combinations to be tried at in the lab using PT nickel. And again, the same story. When you keep the nickel or cobalt in the lattice of platinum, it's showing much better performance than commercial Johnson-Matthey platinum catalyst. And again, here we have performed up to 7,500 cycles, showing the much disabled performance when compared to Johnson-Matthey catalyst. Another, I was pointing out, we have to take care of preferential CO oxidation. When you generate hydrogen from fossils, currently we are using that only, which is having CO gas is much higher. So we need to take care of selectively remove CO from the hydrogen-rich stream. And again, people are using platinum here. So we have developed a core cell catalyst of this one. So our idea is to minimize the platinum consumption for these applications. So what we have done is we have developed copper surfaces through galvanic reaction. When you keep, because of the favorable surface redox potential of the precursor, when we mix with the platinum precursor, platinum salt will be deposited on the copper surface, and eventually when you are eating, you will be getting the different structures. And as usual, we do typical characterization, both XRD and TEM, and we ensure that whether the structure is formed or not. And this is the reaction that we targeted. The hydrogen and the CO is mixed, and the presence of oxygen should be like converted into hydrogen and the CO. So again, various characterization that we have tried, and this is the typical CO conversion. This is the commercial platinum. This one, when we give it the coastal structures, is showing even less than 50 degree, is showing that selective CO removal performance. This is hydrogen concentration up to 300 degree. There is no hydrogen compromise in this catalyst that we have selected. We have prepared in our laboratory. Generally, low temperature is always better for this, and we have prepared the prepared catalyst showing that say CO selective oxidation at the given temperature window. And we also increase the oxygen concentration in that inlet, so that whether any differences in the CO conversion efficiency. Interestingly, even if you increase the 6% of oxygen in the inlet, it's not showing any CO conversion is happening, and hydrogen conversion is not happening in up to 200 to 250 degrees centigrade temperature. That means increasing that oxygen concentration in this hydrogen rich stream, CO can be selectively removed. That is the takeaway message from this experiment. And we have done up to 5 days the stability, and quite stable. We can selectively remove CO gas, and when compared with it's almost showing that, although slight compromise is there, but this is reasonable to have the durable performance. And again, all structure stability and all the fourth morphology that we ensured, and PTCU coastal structure is showing having the potential of for the removal of CO from the hydrogen rich stream. Completely platinum free. Here we have selected intermediate alloy space of PDCU that we prepared for the same applications. It is again having the important potential to selectively remove CO from hydrogen rich stream to CO2. So this again, if you see this in alloy phase of this, showing much better activity even at very low temperature. So that is the energy. Energy penalty is much lower in this case than pure platinum. So achieving alloy or intermetallic phase is a promising for these things. And again, very interestingly, nowadays the people are targeting to create CO and hydrogen to methane, which is important. And the target catalyst that we developed showing that higher temperature range is showing the methane selectivity. So why the plot that lattice-engineered catalyst having kind of unique characteristics. So we have checked using synchrotron facility and whether it's any electronic clouds are different or not. There are several unique features are there. When you expose CO on the platinum surface, it has 3 different interactions on the surface. It's a top, a bridge, and trifold hollow. When you having the intermetallic surface, only you'll be having that only on the surface. So you need to spend a little energy when compared to the pure platinum, so that you can achieve the target reactions. So this is because of this intermetallic phase is you having its structural benefits, so that you can have the target applications. We have done calculation of deep band center of various this one, and compared to platinum, this deep band center is entirely different. So which is actually favorable for target. The most of the automobile exhaust application, this is a story. So with this, let me conclude. And when you tune the lattice of platinum for your target applications so that you can achieve the better performance, and it can show the durable performance when compared with any other, reference platinum catalyst. So with that, let me conclude. Thank you, sir.
Dr. Saravanan, for a wonderful talk, and I'm sure that you'll have good discussions now. People will ask some questions. So before that, we thought we'll have one group photo online, virtual group photo. So then you will also get some time to relax, and then you can start discussing the questions. So I request all of you to start your camera. Maybe then we'll have one group photo, and then after that we will have some discussions. And meanwhile, if you have any questions, please type those questions in the chat box. Then we'll look into that. Lakshmi, one of you can take the photo. Okay, done. Okay, thank you. We're done, Lakshmi? Okay, yeah, Sharon, this is really interesting to look at the 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 technology where we can use some of the lattice-based platinum to address many of these pollutants. So my couple of things is it economical, because platinum itself is also very rare earth
Yes.
material?
Yes.
Whether how do we see whether its application in terms of to look at it large, medium scale, and large scale combustion related application in controlling the air pollution?
Yes, sir. So actually, platinum is the starting point. If you say take the any automobile, and if you see the automobile exhaust, so platinum people are using. So because of our research starts from there only. So whenever wherever the people are using platinum, our efforts to minimize the platinum consumption.
Okay.
So that way we are selected the D block, low cost D block elements. Mostly we restrict copper, copper, nickel, iron. We are see the like electronic structure of that, and depending on the characteristics, accordingly we'll go for the applications. So people are using platinum. That is the starting point, and we try to minimize the platinum consumption. So that's where we minimize the cost there.
Okay. The second follow-up question is how economical is it? Because we talk about in terms of control, if it is an emission itself is having for example, right now if you try to take all the efficient combustion engines and look at the old combustion engines, there the proportionate in terms of the emissions they contribute is quite significant. So whether these technology can be put it according to that, whether the flow rate or the surface area will have some influence on in terms of reducing or designing the system.
This is platinum is already there. It is already coated on diesel oxidation catalyst or DPF, whatever. There are two-way and three-way catalytic converter. People are using platinum, and the technology is already there. So what we do is here we are instead of platinum, because of this advanced materials designing, we keep along with platinum precursor and target transition metal-based precursors. Then we keep the similar conditions so that we can achieve the target phase. So the already the preparation technology, everything is there in the market.
Okay.
So here simply we need to take a little bit more durable and other thing. And in fact, we have one of the catalyst. I use the platinum-free catalyst, strontium ferrite, and it is actually tested the actual engine dynamo of the Tata Indiga machines. We have used it. You have taken that engine at the IIT Kanpur. We have tested that engine and we found much promising performance compared to even commercial platinum. So that work got patented, in fact. So anyway, so the already technology is already there. So simply that people are using coordinate substrate, and we have to take the coordinate substrate and we have to deposit the precursor. You need to subject certain experimental, subject reduction conditions, so that you can achieve the platinum. Of course, automobile manufacturer having the different method to prepare platinum platinum catalyst on the various support, and our method is we have mixed with the target precursor and we keep the reduction conditions dry reduction conditions, and we are also able to prepare roughly 2 to 4 nanometer size, and it's also scalable.
Okay,
So
very good.
we keep simple method. Yes, sir.
Yeah. So the other question which I'm trying to look at it, since you mentioned something about the cycles. So for example, if you look at it, how long it will going to work, whether how the efficiency will going to reduce if I start using it in a particular system, whether it is work for for 1 month or 6 months, depending on the emissions it is contributed, whether it is an high emission vehicles, how long it will work, whether it is a low emission vehicle, how long it will work. Do you have some thoughts or comments on that?
Yes, sir. So again, as if the catalyst we haven't tested for a month together, but what we are generally doing, we take the actual commercial catalyst what people are using platinum, and the same commercial catalyst, and we keep as a reference the similar same experimental conditions we expose, and along with our catalyst, and we compare the performance as well as the structural characteristics, and we see the platinum how it is changing, the same conditions how the proposed or synthesized catalyst in our lab how it is changing, and we see the and compare the characteristics, and we found there are certain catalysts which we developed is showing both structural integrity as well as performance. Of course, there are some catalysts actually fails when compared to the platinum that I didn't bring here, but these are the combinations. Today, what I have shown is it's showing the better performance than commercial platinum. So always we keep platinum is a benchmark performance.
Okay.
Then
Yeah.
we compare in both. Both stability as well as durable performance. Everything we compare as a platinum, and we see that how the things are like changing.
Okay, it's good. So there's one online one question is what is the efficiency during the presence of co-pollutants like sulfur dioxide? It could form sulfate salts that could be attached on the catalysts so that it can reduce the efficiency.
I don't have direct answer for these questions, but again, as I just pointed out, we check the actual commercial engines Tata Indiga. We developed the material. We exposed the same automobile exhaust conditions, both commercial platinum as well as the cathode that we developed, and we see the performance and all the things. Of course, sulfur was the issue, but these days sulfur content is quite significantly lower. That's the reason people are now revisiting the perovskites, for these kind of applications. A lot of renewable interest are there now. But it is worth of trying with using the sulfur-rich oxides, so that how that that better performed catalyst performing, that we is worth of checking. Yeah, I don't have direct answer, but we have checked, the same conditions. Yes.
Okay, actually, in fact, you have rightly said, since we also have low sulfur fuel which is being used in many places, particularly if it is an high sulfur content, then there may be an issue in this aspect. Okay, so I'm just
For sure, when you go for like perovskites and all the things, if it's high sulfur, the catalyst will quickly like deteriorate.
Yeah.
Initially, you'll get the activity, but it will be deteriorate. But because of these low sulfur gasolines are available now in the market, so now people are looking to use this one. Of course, along with a little bit platinum, PGM that people are now targeting now.
Okay. Yeah, that's correct. Any other questions from those who are participating? Any quick questions? Sure. Yeah. Have you made, so although you patented it, whether it has been commercialized, any of this technology?
Actually, we have interacted with Suzuki, and it is supposed to be like a tested in Baleno car actually, but because of our how to say NCR initially we tried to test it at NCR region, and now entire diesel related vehicles now banned in NCR regions, and Baleno stops production of diesel vehicle. So now we moving to like informal, biomedical waste sector. So now we are now using planning. We are testing in our laboratory to use this catalyst. So yeah, so little mismatch of country's policy and our development.
Yeah, should be okay. Maybe there will be one day it will be of some use. Any other questions from any of you who have joined online? Okay, Sharon, I think there are no questions. Yeah, we would like to, on behalf of our, air quality management lecture series. So we would like to thank you for your time, and we hope to see you sometime in the campus, and we'll explore the future collaborations with you. Okay,
Thank you,
and
sir. Thanks for the opportunity again.
yeah. We also take this opportunity to thank all the, for you, the members of this community who are joining this continuously air quality management lecture series and supporting these initiatives. And thank you very much to all of you. And have a nice evening, and see you in the next air quality management lecture series. Thank you very much. Bye bye. Bye, Shravan sir.
Thank you, sir. Thank you, sir.